Welcome to a new video about analog filter design. In this example, we will discuss the Bessel response low-pass filter design. We'll see everything step by step in our calculations and verify these in SPI simulations. Okay, our design objective is shown here. We'd like to design a Bessel response active low-pass filter. We will use the Sallen-Key filter circuit. And finally, we will also calculate the actual stop band attenuation. The specifications for this filter design are shown here. We need to have a maximum passband ripple, which shows as a max of 3.01 dB. This is, by the way, also the gain at the cutoff frequency. The minimum stop attenuation we need is 20 dB, a min. The cutoff frequency must be 1 kHz and the stop band frequency is 5 kHz. So the meaning of this stop band frequency is the following. At this frequency of 5 kHz, we need to have an attenuation of at least 20 dB. So we will see that shortly, how we need to determine that and also how we need to verify that in the SPI simulations. Okay, first step is our transition sharpness. Looking at this cutoff frequency and the stop band frequency, we can see the ratio of the stop band frequency over the cutoff frequency will be then 5000 over 1000 will be 5. This is an important parameter we will use shortly in order to determine the filter order. Now the second step, filter order, is using this graph for the Bessel response. You see here in the horizontal axis are FR, which is our transition sharpness, and this vertical axis you see here the A minimum, which is our stop band attenuation. In this case we need to have an FR of 5, that is actually this line, vertical line, but we need to have a minimum of 20 dB attenuation, and that is this blue line here. So we see an intersection here that is actually given by this dot here, so I can also a little bit zoom in here, you see that more clearly. So you see that also here. In this case we see indeed 5 here and 20. We will see also here the first order line, the second order, the third, etc. And that means we are now with this intersection point, the green dot here, between the first and the second order. Now in order to fulfill the specifications, we cannot go for the first order, so we need to go to the second order, so we need to go a little bit higher. But if this, for example, the line was higher, let's say at 30 dB, then we need to go for the third order. Why? Because then you see that you are above the second order line. So that's actually the reason for going to the second order. Okay, let's go back and continue with our discussion. So having determined the filter order NS2 for FR of 5, we can continue with our next step, step 3, for circuit realization and the component values for that circuit. Now for that we need to use a Sallen-Key filter circuit. In this case we have a second order, that means we need to use a 2-pole Sallen-Key low-pass filter circuit. And that is shown here. You see here the unity gain feedback of the operational amplifier. We have 2 resistors, R1, R2, and 2 capacitors, C1 and C2. So we need to determine the values of these 4 components. Now we can do that in a more efficient way by setting the resistors equal to each other and define it as R. So I now select the value as 1 kilo ohm. Then the next step is the scaling factor calculation. That is then defined by the capital letter C is equal to 1 over R omega C. And this R is what we have selected here. And the omega C is 2 pi times the FC, and FC is our cutoff frequency. So that means 1 over the 1000 ohm times 2 pi times 1000 hertz. That will result in 1.5915 times 10 to the power minus 7. And this is an important value we need to use in order to calculate the capacitors C1 and C2. And for that we need to bring up our Bessel response table. You see here the filter order, the number of sections and what kind of sections you need in your filter circuit. And the first row is about the low-pass filter design, and the second row here is about the high-pass filter design. Now we need to of course have this first row, and there you see for the second order, because that's why we need to design, the C1 over C, that is the same C as we have it here, is equal to 0.9066, and the C2 over C, that is the second capacitor, is 0.6800. So from the table we see actually this ratio and these 2 ratios actually. So C1 can be calculated, just rewrite this, so 0.9066 times this C, and that will result in this value of the capacitor, 144.3 nanofarads. In a similar form, C2 will be then calculated like so. Now we have our capacitors, so C1 and C2, and also our resistors are selected, and we are actually done with our design. Of course, we need to go to the actual stop band attenuation, and for that we need to do some calculations, and this is actually what we do next. Now first we start with the transfer function of our low-pass filter of a Bessel response. That's then given in general by this expression. you see here this t sub n, that n is our order. The n here, the capital letter N, is the numerator coefficient. We will see shortly what it all means. And the denominator here, d sub n, which is given in the Laplace parameter, is our polynomial of this transfer function. And that is then given in general like so. So if you have a higher order, you can use this general expression to create your polynomial. Now for the Bessel response transfer function, we have the coefficients shown here. This is then from first order up to the 8th order. You see here A0 up to A7. So we have 8 coefficients. And this capital letter N for our numerator coefficient. Now in this case you see that is also changing depending on the filter order. Now in this case we have a second order Bessel response transfer function. That means we need to look at this row. Now since we have a second order, that means this will be then d sub 2, and that is then s squared plus a1s to the power 1, which is then s plus a0 only, and that is actually shown here. And looking at the table, that means we need to see that then the a1 is 3 and a0 is 3, and that is actually also substituted in here. Now we have now our transfer function almost done, because we also know what the n sub 2 is. That's also 3 here, so everything is actually 3 by coincidence. And now we have here our transfer function in the S domain, Laplace parameter. We can convert that to the j omega domain by setting S equal to j omega for steady state analysis, and that's shown here. What do? We actually make this S squared j omega in the parentheses squared. That will be then minus omega squared. That's actually a real quantity now. So 3, we place it in front, 3 minus this omega squared, plus this j3 omega. Now we have our transfer function in the j omega domain, so we can use that to continue. And for that we need to first determine the magnitude expression. That's just the magnitude of this expression like we do in the complex expressions, the transfer function. That's actually shown here. So you square the real part plus the square of the imaginary part, add them up, of course, we just said, and then square root of that one. That is what you do for the magnitude of the denominator. The numerator was real, so we just keep it as 3. And that is now this expression. And now we need to define or go to the omega where you have the cutoff frequency. And that is defined by this. We see here the T2 evaluated at 0, which is our DC gain for the low pass filter. That is 1. Why? Because look at this expression, or that expression, doesn't matter, or this expression. If you substitute here S is 0, you get here 3 over 3, which is 1. So that is correct. You can also see it from here or from here. So everything will be then result in 1. Now we need to equate that. So this one will be then here, and that will be then equal to that one. If you now solve this using a solver, or you can do it by hand, that will give you an omega which is 1.36165 approximately. This is actually a bit different in a more exact way, but this is good enough, and that will be now defined as t sub n, and that is the time normalizing or normalization factor. And this is an important parameter we need to use in order to continue with the calculation of the actual stop attenuation. Next up is the scaled transition sharpness that is given by the capital letter omega sub r, and that is now defined as the value we already know, which is then fs over fc, which we call the small letter fr. Now that will be then multiplied by this time normalization factor or normalizing factor. So it will be then this 1.36 etc. times this 5. We'll get now here approximately 6.8. Now what do we do with this value? Now we are ready to calculate the actual stop and attenuation, and that is given by this expression. A minimum is minus 10 log n, capital letter N squared, divided by alpha squared plus beta squared. So we see here now two new parameters. That alpha is the real part or real value of the denominator of that transfer function, evaluated at that capital letter omega r we just calculated. And beta in a similar form is the imaginary part of the denominator, again evaluated at that omega, this capital letter omega r. Now the d2 in j omega domain is just this denominator here. You just copy that. You see the real and the imaginary value. How do we calculate that? Now in a more mathematical way, you see that here, and you take this 3 minus omega squared, you substitute here this 6.8083. That will result in minus 43.35. And a beta in a similar form, you take here 3 times this 6.8083, and that is then 20.42. Then we can calculate now our actual stop at attenuation. This is of course here 3. That is of course also from this transfer function. Now we are almost done. Just substitute here the values you get now here. 24.07 dB. And this is indeed larger than the minimum required 20 dB here. So indeed we will fulfill our minimum stop and attenuation specifications. Okay, let's now go to the simulation results and check our calculations. This is the Bode plot. You see here the curve in blue, the frequency in the log scale, and this is the gain. And this circuit is our circuit in the T9Ti SPICE simulator. You see the resistors and the calculated capacitors. And this is the calculation for our A minimum again, to bring it up here for completeness. What do we see? We see here the low frequency gain is 0 dB, of course, because that's the unity gain feedback, and for low frequencies this will be just a unity transfer. We see the cutoff frequency or the gain of -3 dB, so you go from this baseline down by 3 dB at 1 kHz as required, so that's also correct. And at 5 kHz we see here a gain of -24.05 dB, very close to what we have calculated, also more than what we need to have because the attenuation is indeed larger than 20 dB. Alright, this was our example considering the Bessel response active low pass filter design. Use the Sallen-Key filter circuit. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.